Is Evangelos Papoutsellis from STFC on tomography reconstruction using CIL.
Thank you, Simon. Thank you for the invitation. Yes, I'll talk about tomography reconstruction using CIL. So, CIL is a core imaging library. Have some introduction and design for CIL. When I move to optimization framework that we have in CIL, present some case studies and try to connect the final section, some things from the previous talks. So CIL is an open source Python library, object oriented for solving image inverse problems. We give emphasis on tomography application for challenge data set. It's high flexible. We can test it in different imaging problems. We have a simple API for math to code translation for optimization problems. We have this for large and real application. So it's Apache v2 license and it's actually developed on this GitHub repo. CIL is funded by this CCI project that Chris mentioned, so the Collaborative Computational Project in Tomographic Imaging. There are many CCPs. We funded by the CCPI, the Tomographic Imaging, and now we are in the third stage of this project. PI is a few contributors from Manchester. We have Martin Tanner from Manchester, Jakob Jorgens from EDU, Jay Warner from Warwick, Leon Svensson from Swansea, and we have Eduardo Pascal, Gemma Hardell, and Laura. We are a software developer working at STFC. So who is CIL4? Mainly CT experimentalists. We like the user to write quickly CT processing pipelines, optimize standard algorithms for large data, and also for imaging processing specialists to easily implement new reconstruction algorithms and assess them against existing ones. Yes, so everything is still is object-oriented, so we have a lot of classes following the Pythonic way to develop the software. So we have this kind of modules, the I/O, input, framework, processors, utilities, optimization, plugins, and recon. So the framework is the most important one. So you can think of the data container as NumPy arrays with information coming from the scanner. And we have also the acquisition data. It's related to the acquisition data that's related from the scanner and the geometries. Then we have some classes that are to read data coming from the scanners, pre-processing step, like remove reduction or correction for the center rotation. Some utilities, visualize or interactive visualization, which is iSlicer. Yeah, and optimization will have different algorithms, functions, and operators. The plugins. So for the plugins, we have the projection operator. So the projection operator for the tomography application, and we rely on Astra Toolbox and Tigre. There is also another plugin for GPU accelerated methods, proximal of TV or proximal direction of total variation, and Tomography to simulate some data sets. And also we have a recon class to do FPV and FTK reconstruction. So the idea is to have an easy for the user API. So after we do the scan, we use this data reader to read the data from the scanner. We convert to absorption, the data of absorption, and then we correct for the center of rotation. And then the user can, with a simple command, see the geometry of the data, and also can do reconstruction with FPP okay, in this case it's FTK, and see the reconstruction in this less. In particular, we have this optimization framework. So we have this type of objective function that we want to minimize, and we have many functions to formulate different imaging problems. We have, for example, KL for the feedback library for Poisson, L1 for salt and pepper noise, L2 or least best for Gaussian noise. We have this mixed L2 norm or smooth for standard total variation or the smooth version of this. We have many more for the operators. So the block operator is something that Matthias mentioned, is like a stack of operators. For example, we have the finite difference gradient operator to formulate a gradient that can be used in TV. Symmetrized gradient is for TGV, and yeah, we have projection operators for ASTA and TV. Yeah, and at this moment we have this algorithm, CGLS set, gradient set, FISTA, or proximal gradient set FISTA, the ADMF, PDHC, and the stochastic version of PDHC. We have tested SIL in different applications. So in SIL, we can handle different geometries, parallel, cone beam. We can also do laminography. So the idea is in printed circuit boards where we have different exposure along views. We can use this laminography. And we tested that in this data set, the Lego brick. So in classical CT, we have this kind of setup. We have the actual rotation for CT. In laminography, we fill the sample and we do the scan. So well, and another to have this angle for the filled levels. Yeah, and the optimization is quite flexible. The optimization setup is quite flexible. We can have basically different regularizers or constraints. So first one is least squares with no constraint, then with no negativity, with symmetry but no negativity, and again no negativity. And you can see the results here for this Lego example. I think I will skip it then. Simple case. Yeah. Yeah, another example is the hyperspectral CT. So in the Manchester, we have a color-based scanner, so it has spectroscopic detectors. So the idea is during the scanner, we collect two pieces of information: the energy and the position for each photon. And for this, we tested on iodine stained laserhead, and we compared it with the dual energy CT. And actually, doing hyperspectral is much faster than dual energy CT. And for this case study, we use this kind of minimization problem. So SIL is quite flexible to combine different regularizers in different dimensions. So here we have, so this is a 4D data set, so it's 3D plus energy channels. And we add two regularizers, one in the space, one in the spectral dimension. And we regularize, we use TV for space and TGV, total generalized variation, for the spectral. Because in the energy dimension, in the energy profile, we have piecewise affine structure, so TGV is suitable for this. And here you see the energy dimension and also how it's reconstructed per slice. Yes, so SEAL, in SEAL and CPI, we work a lot with another CCP project, the CCP Synergy. So, and this is for medical imaging application. So SEAL and SERF, the Synergistic Image Reconstruction Framework, they have the same API. They use different engines for doing all this NumPy, all this array computation, but in SEAL we rely on NumPy, and in SERF they have C++ implementation for the other. Also in SERF there are 3 other modules for PET, MRI, and registration, and we can use this as operators in SEAL, and we can pass it to optimization framework and use SERF, use the operators from SERF, PET, MRI, and registration, in the optimization framework of SEAL. And we tested this synergy of SEAL and SERF in different applications. So just an OCM reconstruction is coming from SERF, and primal dual PhD algorithm from SEAL with ultra-high divergence plus TD as a regularizer. And the other example was we use the FIST algorithm for MRI reconstruction with no motion correction and regularization, NTV. And then we pass this information to a PET reconstruction problem coming from the MRI. Okay, now about the stochastic optimization. So this year we did a hackathon in Cambridge, and last year we did another hackathon in Oxford. This is a joint work with many people from different universities and institutions. And the idea is to extend the deterministic framework of SEAL to a stochastic one. And this is organized by CCP Synergy, CCPI, and PET++ from Bath. The idea is to implement in SEAL stochastic gradient descent, SAGA, SDRG, and more. Implement the subset data structure for STER and SERF, and establish a benchmarking framework for CT PET applications. So far in SEAL, we have these proximal gradient methods like GD, so smooth objectives, gradient descent, ISTA, proximal GD, and a faster version of ISTA with an additional step for the moment. And we can call this kind of algorithm with these commands using CIL. Now, the idea that we had during the hackathon is not to implement again new algorithms like SAG, SDRG, but use these three algorithms for our stochastic optimization. So if we replace this f of x by the sum one of them for n is the number of subsets, we can replace in every iteration, instead of computing the full gradient, we compute the gradient of a function which is randomly selected from these FIs. And we can have a GD and ISTA and FISTA version for this. And from a design point of view, we name this subset sum function, which is a class function in terms of CIL, and randomly selects an IK function and computes this gradient. Now, if we leave this with gradient of FIK, this is the HGD, proximal HGD, and accelerate the proximal HGD. But also we can replace it with variance-reduced gradient estimators like SAG, SAGA, and SDRG. So we have now like a plug and play framework for different stochastic gradient estimators. So the user can select a subset sum function and GD is an crystal that already exists in C, and can play around with different combination and test it in, do a quick benchmark in these problems. Now, this is very recent work. So before we have f of x and g of x. Now we have the composite part, which is the conduct dual algorithm or the primal dual three operator splitting. And for that, we have this assumption that the f should be L smooth, proximal g, and the composite function h. So this is very similar to primal dual. So you have your proximal in your g function, the proximal for the convex conjugate of h, but now you have a gradient step for the function f, and then the update at the end. So the idea is to, instead of computing the full gradient at each iteration, we compute a reduced for a randomly selected function. So they were in 2016. They proved some convergence result for the case where A was the identity. Then in 2018, the same convergence result, but when A is not the identity, and they use gradient estimators. And very recently, there is the same analysis, but both for A not the identity operator, for gradient estimator, and variance reduced estimator. And the idea is to replace the gradient by variance reduced estimator. And in the same setup, we have again a mixed plug and play approach. The user can select a subset sum function and combine this primal dual three operator splitting with stochastic variance reduced methods. So yes, we tested this on a simple least squares problem. So X star was computed using another library for convex optimization. And we have GD, phi star, SDD, which is this yellow thing, and it's quite oscillating. We can use SGD with decreasing step size, Saga, and Saga. And then SGD star is something that we can find here in this paper. So it's not used in practice. But when comparing different stochastic algorithms, it's nice because that's like the optimal convergence we can have because it's not used in practice because we have these differences coming from the optimal solution that we yes, and because with all this plug and play framework, we can easily compare deterministic versus stochastic algorithms. So we have ISTA-FISTA for this problem. So this is from the lizard dataset. They will use 30 subsets. Every algorithm is initialized by an FBB reconstruction, and the X star is computed with FISTA after 1,000 liters. And the first four are the deterministic ones, so no stochasticity. Then we have the proximal version of SCD, the proximal version of SAG and Saga. Then we have the proximal version of the proximal version of Saga accelerated. We have the SPDHZ, Matthias, and we have the primal dual free operator splitting with Saga as the gradient estimate. And it looks like the PDF of Saga is faster. What's now? 8 minutes.
You started, yeah, 8 minutes.
Okay. The final part. So this is for a better reconstruction minimization problem. So we have the Kullback-Leibler divergence. We have a TV prior and we have a non-negativity constraint. So the idea is we have the primal dual free operator splitting. We have three legs, F, G, and H. F is the L-smooth, G is the proximal, and H is the composite one. And we see that we can extend this using variance-reduced gradient estimators. Now we can do this with SPDAG. So in SPDAG, we have a randomness in the dual update, so the convex conjugate of HI, I select randomly in its iteration. But we can do this with SPDAG and have 3 layers. And in a recent paper by Compet, they suggest that sometimes it is useful when you, so ideally, logically, you take the gradient for the smooth part and you take the proximal for the non-smooth part. So in this paper, they say that sometimes it's faster when you take the proximal operator for the smooth function. So I use the same idea here, but now for the stochastic part. So we have a sum, so n is the number of subsets, but now I split the data fitting term into the first m subsets, the first m functions and m subsets, and then from m to n-1, it's the other. So here f of x is the non-composite part. So the part that will use the gradient of f of x. And here is the part of the composite part which will use the proximal step. So in every iteration, we have a random update, a randomness in the dual update. And also we can use the randomness in the primal update using stochastic estimator, gradient estimators for the f of x. So here I tested on this for algorithms. So we have SPDAG, so randomness in the dual update. The purple one is the primal dual with 3 operator splitting, and I use the Saga estimator for the gradient. And then it's the SPDAG with 3 operator and Saga. So again, the H part, so the H part is the composite part where we use the proximal, and F is the smooth part where we use the gradient. Not to give a full gradient in its iteration, but the gradient for a random selected function. And also we can do again like a plug and play. We can test it with Saga and SCD. I did only SCD and Saga. And this is for all these plots is for the simulated 2D thorax size from SEF with 8 subsets. Every algorithm is initialized from an OCM reconstruction, and the X star is after T star with 1,000 groups. Okay, in summaries, SEAL is an open source Python library, object oriented, for solving image inverse problems. We have emphasis on tomography applications, CT, PET, and MRI. It has an easy API and can be adapted for different imaging applications. Recently, we have established a plug-and-play framework for stochastic optimization. It's simple to start with because it's API, and we have tested it for real and large application. Here is the website of our library, our documentation in this link. We have a Discord channel. Everyone is welcome to join. This is where we usually ask questions or propose new ideas. And thank you for listening.